After seeing all this analysis, we must finally answer a question. How do we deal with the problem of register allocation? We have figured out the flow of a program. We know which variables are live where. Now we have to figure out how to allocate registers for each of the variables. We are going to solve this problem by using webs, graph coloring and splitting, and the end result will be that many values will get registers but some won't, and they will have to be spilled to the memory and will have to be loaded and stored out of the memory when they are needed. So students, welcome to the second part of this embedded software class, and what we are going to learn in this in particular is how those instructions and embedded processors that were designed in the first part of the course are used by the compiler to generate highly optimized code. Remember that embedded systems need very high amount of optimizations because of energy constraints, because of code size constraints, and because of high performance demands. And to begin with, we are going to see the overview of a compiler structure here. So as you saw in the lesson 7, which was the overview of compilers, what we have is a compiler front end, which consists of a parser, scanner, and semantic analysis. And the job of these is to verify if the code is correct in terms of its syntax and semantics. And then if it is, to generate what is called as an intermediate representation. And on this intermediate representation is what we do code generation. In this particular second part, we are going to focus on the code generation. And in particular, the code generation consists of first selecting instructions for each of these operations which are present in the IR or intermediate representation, and then doing register allocation on them, and then finally doing instruction scheduling to arrange those in a highly efficient manner to hide the latencies of the architecture. The latencies are present in two types of instructions typically: load stores going to the memory and branches which create a bubble. So focusing on the back end, the idea is to be able to generate the assembly instructions from the intermediate representation. And as I mentioned, these steps consist of selecting the instructions for the different operations, doing register allocation in which we allocate registers to the operands, and then finally scheduling these instructions for efficient accesses. One of the key steps that is involved in efficient code generation is to determine which of those values are given registers and which of them reside in memory, and this step is called as register allocation. There are several substeps that are involved in code generation. One of the first substeps is to take that intermediate representation, which is in quad or triad form, and convert it into a control flow graph. This tells us which instructions execute inside a basic block and how those basic blocks flow from one to the other. The graph that is generated in this particular process is called as control flow graph, and it shows the control flow of the program from one basic block to the other. The next step that is involved in this process, especially in the register allocation, is to perform the data flow analysis. The data flow analysis allows us in this particular case to determine what is known as liveness. Liveness tells us which variable is carrying a value from one point to the other to be used at the next point. This analysis is the precursor to a very good register allocator. And finally, after those live variables information is captured by the liveness analysis, we are going to actually decide which of these variables get registers and which of them will be residing in memory. And in this lesson, we are going to focus on this particular aspect called register allocation. So in other words, what you should be reading first is control flow analysis followed by liveness analysis in self-study lessons prior to this. And so with that knowledge, now let us focus on register allocation, which tells us which variables get the registers and which do not. Now back to the quiz. So register allocation is a must for CISC architectures. That statement is false. You know how CISC architectures work. All the operands are in memory. There are long instructions which fetch the operand, operate on those values, and store the results back into the memory. That's how the CISC or complex instruction set architectures work. And so the register allocation is not really needed for these architectures. Let's look at the RISC architectures. The answer is true here. The register allocation is a mandate or is a must for RISC architectures. Again, remember how RISC processors work. They bring all the values from memory into registers before they can operate on them. In other words, you cannot operate on a value which is resident in memory directly. You have to first bring it into a register and then only you are able to operate it. So these are also called as load store architectures for that matter, and therefore we must allocate and use registers maximally here. VRIW processor or VRIW architectures, the third statement says register allocation is a must for them, and it is true statement because remember in VRIW architectures, the compiler needs to have a control over latency and it can figure out the latency better if the values are resident in registers. We know that it takes a fixed number of cycles for those values, and therefore VRIW architectures also need a good register allocation so that they can efficiently do bundling and scheduling of instructions. And finally, the last statement is register allocation saves energy on embedded processors. This statement is also true. Remember, efficient register allocation means we are operating on values which are in registers rather than going to memory frequently. And since we are not going to the memory frequently, we save a lot of energy, especially in caches. You will see that in a later lesson, we are going to exploit this particular behavior to save energy. So students, having studied different types of processors, CISC, RISC, VRIW, and other embedded processors, let us see if we understand the role of register allocation with regard to each one of them. So here is a question for you. Which of the following statements are true? Mark all the ones that are true. The first statement is register allocation is a must for CISC architectures. The second question is register allocation is a must for RISC architectures. The third statement is register allocation is a must for VRIW architectures. And the fourth one, register allocation saves energy on embedded processors. With the knowledge of how these different processors and architectures work and how the register allocation works in terms of keeping values in registers as long as they can be, please answer these questions. Go ahead and mark your answers now. Let us first motivate the importance of register allocation through a simple example. Consider the problem of adding two numbers together. We have two options. First is, if we decide to keep these numbers in memory, here is how the assembly code would look like. Let us look at this code and understand what it is doing. First of all, SP is the stack pointer and 4 is the offset. So the first operand is at offset 4 in the stack and is loaded into register R1. Similarly, the second operand is at offset 8, again in the stack, and is loaded in the register R2. So these two instructions show us that those operands are in fact in memory and are loaded. Then an add instruction adds those two registers and has the result generated in R3. And finally, we have a store to put the value back into the stack location at offset 12 in the memory, and this is that store instruction. So you can see here for the simple example, we have two loads and one store which are going to the memory and then one add operation. As against that, we have an option 2. Suppose we decide to keep those operands in registers and we have those already in registers R1 and R2. Then we have an add instruction and we also decide to keep the result also in register. That allows us to get rid of all these load stores going to the memory. Of course, for generating this option 2, we have to allocate registers. We have to keep this operand which is at this particular stack location and keep it in register R1 and the second operand into register R2. And in order to do this particular thing, we have to carry out what is called as register allocation. We can also store the results without going to memory, pretty much carrying out all partial operations, partial results. They're all staying in registers and we rarely go to the memory to store them. This particular act is called as register allocation. Why is this particular code efficient? As you can easily see here, because we are not going to memory, we do not have load stores, we do not have latencies, and we have a very highly efficient code because of operating on the values on registers. So before we actually get into the register allocation problem itself and see the techniques, let us understand from a computer architect's perspective what is going on in terms of registers. First of all, there are few registers available. Typical number of registers that are available are 32 integer registers and 32 float registers. And then some registers are used for particular purposes. For example, the registers can hold either an integer or a floating point, and so there are different registers for integer operations and different ones for floating point, typically 32 for each of these operations. Then certain operands, such as double, for example, need very wide registers, and the wide registers are synthesized by what is called as double word registers, that is by coupling two registers together, which is also called as register pair. So R0, R1 could form maybe a register pair which could hold a wide operand, such as double. There are special registers which are used with special instructions. For example, we have seen this earlier. If we have predication present in the execution of the branches, then we have separate predicate registers which hold the outcome of branches and which are used for nullifying a set of instructions. Many times we have a separate register which carries the target of the branch, which is also called as the branch register. As you know, the functions execute on a stack, and all the arguments to the function and return values from the function are maintained on the stack. And so we have a special register called a stack pointer, which tells us the area where all the local variables for a given function when it is called are present, and that stack pointer also gives us a return address and also holds some other information for sending the values to the function and getting the values from the function. This particular area of the stack is called as activation record, or called as AR, and the stack pointer typically points to that. Finally, many times we have a special register R0, which is the load register for holding the whole program, and in a particular area of memory, when the program is loaded, this register is initialized to the actual address there. And finally, last but not the least, we may have some registers specially designated for string manipulations, such as string comparisons. And the correct answer is no. Let us look at the reason behind this. The main reason why this allocation is not correct is as follows. A of I may be sometimes same as A of j. That is true if the index I is same as j, but not always. This means A of I and A of j are two different locations, and they may not have a data flow between them. That is, the value of A of I will not be used in A of j here. The code on the right hand side, on the other hand, is always implementing this data flow, that is, taking this particular value and assuming that it is always equal to A of j here, and therefore it is incorrect. So to assume that a may data flow is always true is a wrong assumption, and therefore the code is wrong because it will pass on a wrong value to A of j here by using R1 here. Now this also illustrates to us a very important problem that occurs in register allocation. Remember, we already talked about pointers, but the second important entities which are not possible to allocate in register that easily are the arrays, because we cannot easily figure out at compile time if A of I is always equal to A of j or not. If we cannot figure it out, we simply have to store a value in the memory and load it here. So that's why we'll incur lots and lots of load stores inside this while loop, and that is why the code will become inefficient. And this is kind of very unfortunate situation, because you can see that inside a loop we would have loved to remove a store and a load here, but we cannot, because at compile time we cannot figure out this is always equal or not. Remember, unless we really prove it is always equal, it will be incorrect to implement this data flow by giving the same register here. Now let's really understand the foundation of register allocation in terms of what is it really doing. So what I have here for you is the source code of a program which has a while loop in it and two array accesses. A of I is being written and A of j is being read inside the loop. And on the right hand side here we have a register allocated code which is implementing the write of A of I through a load in register R1, and the same value is being used now for A of j using the same register R1. The question that I have for you is the above register allocation correct? Check yes or no. Please go ahead and mark these answers now. So now let us understand how exactly do we carry out the register allocation. In any register allocator, we have two steps. The first step is what determines which of the values should be in registers at each of the execution points. Register allocation determines which one of those variables, which one of the temporary values which hold the temporary partial results, which of those constants should be held in registers, and which ones should be held in memory. So in other words, this particular phase gives us a binary decision. This particular variable should be allocated in a register. That particular variable, on the other hand, should reside in the memory. And the second phase is called as register assignment. In the register assignment phase, we actually decide which is the exact register that should be given to a variable which is designated to be in a register. For example, we say that variable A should be given a register R5. That's what happens in this particular phase. So what is the goal of register allocation phase? The goal is to minimize the traffic between the CPU and the memory. In other words, maximize the number of values which stay in the register for the longest duration. That way, we don't have to fetch them again and again from the memory. As you can very well imagine, this is the optimization which has the highest performance impact. This is true not only for embedded systems, but also for general purpose processors. In embedded world, register allocators, of course, assume very highly critical role because all three parameters are affected by the register allocator: the performance or the speed of the program, the code size, because if you have too many load stores, the program becomes long, and then finally the energy efficiency, because if you're going to the memory and performing memory operations very frequently, your program is very energy efficient. So the better the allocation is, the better is all three parameters for embedded systems. Now, one other complication in embedded systems is that we have very few registers. I mentioned earlier that we have 32 registers for integers and 32 for floats in general purpose processors. In embedded systems, this number could be half of that. That is, we could have just 16 registers. Why is that? Because many of our instructions are small, many of the hardware is simple. We do not have space to hold so many registers on the chips sometimes. This puts more pressure on the register allocator to be better, because how to allocate just those 16 registers is far more difficult than allocating 32 registers. Before we get into a detailed discussion of register allocation, let's review a few fundamental definitions that you must have seen earlier in the data flow analysis for liveness. So these definitions are applicable to the variables that are getting defined. That means we have statements such as A is equal to such and such. Here is a definition for this particular variable. And we say that this particular definition is generated at this particular point if we have such a definition present. We typically give it a label. That is, if this is an A which is present at instruction place 5, then this particular one will be called as A5 to show that this is a particular definition of A present at location 5. The second definition that we will be looking at is called as kill. Kill tells us that the older definition cannot proceed further from this particular point and is killed at this particular point. Again, let's take an example of that A5 being present here, which is a definition of A at position 5. So any other definition of A coming into this particular point from above is not able to go through because it is shadowed by this particular definition. So if there is A defined over here, which is carrying a value 10, and if we look over here what value A is carrying, and if A5 were to be equal to 5, then you can see that this definition of A equal to 10 is no longer available over here because it is killed by this definition of A. Remember, A5 is just our nomenclature. it's really a equal to 5, which is present here, and we are just designating it to be a5. So this particular definition of a equal to 10 is no longer available here and is set to be killed. The third one is just called as definition. So whenever we have an assignment to a value such as a is equal to 5, we say that we have a definition of a present here. And again, as I mentioned, we give it a placeholder. If it is occurring at place number 5, we say that this is a5. So this is to distinguish a being defined at this particular location 5 as against some other location. And if a were to be defined again at a location 10, we would call that particular definition as a10. In other words, assignments to different values at different program points along with those labels generate the definitions which are specific to that program point. Use. Just as variables are defined at different program points, they're also used, and the use typically designates the use of a value on the right hand side. So let's say you have a is equal to b plus c. We can see here that b and c are being used at this particular program point, and those are the uses of b and c. Having seen definitions and uses, now let us see what is called as liveness. Liveness tells us that at this particular program point, the variable is carrying a value which will be used somewhere in the future. So for example, if we had a definition of a, which is a is equal to 10, and then we have few statements, and we are using value a at certain point later on in terms of adding it to another variable b, you can see that in between we are carrying a value in a, and we are going to use it further down somewhere, in this particular case in a plus b. So a is supposed to be live at this particular point. Why is it live? Because it is carrying a value which is going to be used, which has a use coming downhill somewhere. However, if this was the last use of a, there was no use of a after this, and we had yet another a defined after this, you can see that this particular a is not being used after this particular point here. So in other words, for this point, the a is dead. And that brings us to the last definition here. When is a variable dead? At that particular point, a will never be used after that particular point. Another a could be defined, and therefore the current a is no longer being used anywhere downhill from that point. If that is the case, we say that a is dead at that particular point, as shown in this example. Now let us apply these definitions through a simple example that is being shown in this slide over here. As you can see here, we are assigning a value to S1. We are assigning another value to S2. Then we are adding S1 plus S2 and holding a value in S3. Then we are adding 1 to the S3, holding that value in S4, and so on. We also have a product of S1 and S2, and then finally we have S1 times 4. So these are the sequence of instructions which are executing one after the other as shown over here. Let us see if we can find out the liveness information and live ranges that are associated with these definitions. So as you can see here, let us analyze what is going on with regard to S1. S1 is getting a value here, and then flowing down over here. This value which we have put in S1 is being used in this particular place. So this is a definition of S1, this is the use of S1. Further down, again we continue to do this, and we have yet another use of S1 over here. Now in this particular code excerpt, we do not have any further uses of S1 after this particular point. So you can very well see that between this point and this point, we have a value which is being carried in S1, which is going to be actively used in this particular range. And so this is called as the live range for S1, which starts at this statement and ends at the statement at S5. Why is the live range ending here? Because from here onwards, there is no use of S1. There is nobody who is going to need the value which is in S1 from this point down, and that's why the live range ends here. Why is the live range not extending before this? Because this is the first value which is being loaded, which is being used. So any other value which is being present in S1 is not being used before this. And so at every definition, the live range really starts, and as the last use, it really ends. Okay? So the thing to keep it in mind is a live range starts with the first definition. It starts with the loaded value in that name, and it keeps going on and on and on till the last use of that name. After the last use of that name, there is no use of that particular value, and therefore the live range ends there. Similarly, if we apply this technique to S2, we have the live range starting at the definition of S2 and then terminating at the last use of S2, which is over here. So that's why the live range extends from the second statement until the statement of S5. In case of S3, you can see that the live range is very short because it starts here and ends right at the next statement because there is no use of S3 after this particular point. In a similar way, for S4, the live range starts here because there is no value that is being used which is in that name before this. So the first definition point is when the live range starts, and at the last use is where it ends, and therefore we have S4 holding the value, starting the range with the definition, and the range terminates at the last use of S4. Similarly, S5 you can verify, that is implicitly has certain use in this particular case over here, and S6 will potentially have some use down from this particular point, and that's why these ranges are partially shown over here. So we have to find the interference now from the live ranges, and what we are going to do is finding out that S1 and S2 are going to overlap in certain program point. Similarly, S2 and S3 are going to overlap. S4 is going to overlap with S2 and S1, and so on. So if we do this calculation of which range is overlapping with what, and if we decide to hold that information in terms of a graph, that is called as an interference graph. For example, S1 and S2 interfering is shown through an interference graph as follows. S1 and S2 is interfering is shown by this particular edge. Similarly, S2 and S3 are interfering, and if you notice this, S4 is interfering with S1 and S2. So S2 and S3 should have an edge, and S4 should have an edge with S1 and S2. So S3 has an edge with respect to S1 and S2. And you can also see that S4 has an edge with regard to S1 and S2. In a similar way, you can verify that S5 interferes with S4, but none of the others, and S6 in fact doesn't interfere with anybody because it has no overlapping ranges with the other parts. This graph is called as interference graph, and next we decide to do a coloring on this graph, allocating them registers. Now you can see that we have an interference graph which is from the same example using those live intervals and their overlap. This is what we came up with in the last slide. What we want to do now is to give registers to them. How do we give registers? Let us understand what is going on here. Let us assume that we have 3 registers, green, blue, and pink. And if we hold, let us say S1 in a particular register in a live range, that value is present in that register. So therefore, that register is not available to any overlapping range, because if we put another value in that register, the original value will be wiped out. In other words, the nodes which have an edge cannot be colored with the same register. That's a simple principle that we apply, such as S1 and S4 are overlapping here. This is S1 going all the way, and here is S4, which is going from the definition to the use. These are the 2 live ranges which I have shown. And if we give a value in a register to S1, which is going to carry it from here to here, we cannot load that with S4 because it will destroy that original value and we'll no longer be able to use it over here. So that is the concept of overlapping live ranges, which is shown here by this particular graph as well. In other words, if there is an edge between the 2 nodes of a graph, they cannot share a register. So what do? We try to give a register, and we make sure that we give a different color register or a different register to those nodes which share an edge. So let us say we started by giving a register R1 to S1. Now over here and here, we cannot use green register. So we'll go ahead and use the next one, which is pink register here, R3. Now, if we are using green here, if we are using pink here, both are not available for this one because this has an interference and so does this. So both green and pink are out here, so we'll give it a blue. And in a similar way, if we keep proceeding, now if we have pink here, either one of the blue or green would be okay here. In this particular case, we have decided to give it green. And since this guy is not connected to anybody, it's standing by itself, any register would be just fine for it. In this case, we decided to give it blue. So what has happened here is, as a result of this, each one of these values is held in a given register. R1 is holding S1, and so we have the result being loaded into R1, and we are using that result from R1 over here and here. R2 is holding S2, and at this particular point we are holding 4, and again that value R2 is being used here and here, wherever S2 was being used. And similarly, S3 is being held in R3, that result is being held here, and wherever S3 was being used, we are now using R3. So you can see that this whole code which is sitting here is now completely evaluated in the registers by this particular process. We do not have to load these variables from memory through load stores and so on, because we are holding those values in registers. Now you can ask me this question: how many registers were really needed for this? For this particular purpose, we needed 3 registers. Many times, of course, we have fewer registers than the number of values which demand registers. And that makes the problem interesting, because now we have to decide which one of those values is not going to get registers. And that is the goal of register allocation. So now, having defined the main goal of register allocation is to how to hold many values which are demanding registers into only 32 registers or 16 registers. Let us go through steps that are involved in doing the register allocation. As you have seen earlier through an example, the first important thing to do is to determine live ranges. The live ranges tell us where does the definition starts, the first point at which a value is held in a name, and where does the live range end is determined by the last use of that name in the program. So in other words, it tells us that until that particular point, that name is bearing a value which will be used somewhere after that particular program point. The interval between the beginning and the end is called as the live range. We have seen this through an example in a simple basic block in which the instructions do not have any control flow associated, but in general, there could be a control flow associated, and what we call as a web needs to be determined, as we will see. In later part of this lecture, we'll define a web which will tell us how these points between definition and uses are tied together to form a complex structure which flows between different basic blocks, which ties them together between the first point of definition and the last point of use, and is called as a web. The next thing to determine, as we saw again through an example, is called as overlapping ranges. Again, remember, in that simple example, we're trying to find out if 2 ranges are overlapping at any particular program point. This was important so that we could note this relationship in terms of an interference graph so that we don't give the same register to those interfering values. If we give the same register to the interfering values, they will overwrite each other and the program will be wrong. Now, having built the interference graph, the next thing that we are going to do is, on each of the live ranges, which is called as a web across different basic blocks in this particular case, we are going to find out the benefit of keeping that web in a register through what is called as a spill cost. What is a spill cost? Spill cost simply tells us how many definitions and how many uses exist in that range so that we can avoid those many load stores. And that's the benefit of keeping that web in the register. And finally, the critical step here. This step decides which webs get a register and this particular process is called as allocation. There are many different algorithms. We are going to see one of them which determines that some webs get a register, some others do not get a register. Now sometimes we'll also see that the whole web may not get a register, but a part of it could still get a register. In such cases, what we'll be doing is web splitting, determining that part which can be kept in register, and we'll go ahead and give it a register, and the other part will keep it in memory. Finally, we'll be carrying out assignment of actual registers to the web. It's also called as coloring or assignment, to determine that, for example, R5 is being given to S5 and such. And then finally, we are going to generate the code including spills. What is a spill? If a value was held in a register, but subsequently the register was taken away from that value, we have to store it in its own memory location, and that is generated using a store, and that is called as a spill. This particular statement is false. The reason for that it being, it is unsafe to keep all the variables in registers. For example, if we keep a given variable in a register and a pointer points to the memory location of that particular variable, accesses it and modifies it, then the value in the register will be stale and incorrect, because the new value will be there in the memory and the old value will still persist in the register. In such cases, it is unsafe to keep those values in registers, because we'll get access to the old value and not the new value. Thus, the variables that can be modified by pointers, also called as alias variables, cannot be kept in registers ever. Now, during compilation, the compiler cannot know whether a pointer will modify that value or will not, because we cannot determine if pointer will go to that variable's location. So what we have to do is find out if a variable could be potentially aliased. In other words, a pointer could potentially go to it and modify it and exclude such variables from register allocation. We've seen the importance of keeping values in registers, and we want to have a large number of registers for keeping those values. Now here is a question which tests your knowledge in terms of whether we'll be ever able to use infinite number of registers available, and we'll have exactly 0 load stores if we were able to use and keep all those values in registers. So here is a quiz. Let me read the statement and mark your answers if it is true or false. So here is the statement. If we had an infinite number of registers available in a given processor, all the variables in the program will be allocated to the registers. So we'll have no variables resident in the memory. In other words, no load stores will be incurred because of variables not getting a register. Is this statement true or false? Check the correct box. Please go ahead and mark your answers now. So students, now we want to look at webs, a way to extend the liveness analysis across basic blocks. So as you saw in the previous example, in this particular lesson, we had the starting point of a live range at a definition point, and the last use point is where we completed the live range, and the register was given out to the whole live range, which was in between these 2 points. But now the question is, what if the definition is in one basic block and use is in the other basic block? How do we compute these live ranges? And here is where the concept of webs come into picture. Our starting point is still the same, that is, we start the web or the live range at the topmost definition points where the value is loaded into variables, and the last use point is where we'll complete or end the webs. However, things get a little complex because the webs are spread across basic blocks. So one of the key points in terms of determining the web is it connects the definition to all reachable uses, because potentially this definition can feed values to all those uses. And so a given use, on the other hand, may also be fed by multiple definitions, and all those definitions and the corresponding uses should be put into the same web. Because guess what? If we do not put them in the same web, we will have incorrect program semantics. Imagine this simple situation which is shown over here. So we have a use of this variable v in this basic block. We have v being defined in another basic block over here, and we have v being defined in yet another basic block here. And these 2 definitions feed to this use over here. If we put this use and this definition in one web, but leave out this other definition being put into the same web, we'll give out one register, let's say R1, to feed these values, and we'll have R2 for this particular definition. But guess what? This V will not receive proper value from R2 because the register is R1 here. That is why all these three should be connected together into one web, and that's the essential part of defining a web. So as shown by this particular example, the definition and all reachable uses and the other corresponding definition, they all must be a part of the same web. And so what is the web? It consists of all definitions that reach the same use, and also all the uses that connect to a given definition. So it's a transitive closure of what we call as DU chains across the basic blocks, and that defines a web. We are going to look at certain examples to make this concept clear in the next few slides. Let us look at the concept of webs as we have seen in terms of the definitions. How does it look through an example? So you can see that we have a definition of y, which is feeding the value to a use of y somewhere down, and these two are connected by one single web, and we call this as web S1. You can see that we do have another definition of y and another use of y, but this use of y is not reached by this particular definition of y, nor that use of y is reached by this definition of y, and therefore we just connect this definition of y and that use of y and call it a separate web. So you can see that in this particular process we are untangling the definitions and uses. The ones which are reaching each other are a part of the same web. However, the ones which are not reaching each other are kept separate, and they form separate webs. Similarly is the case with x. You can see that this definition of x is reaching that use of x, so they should be a part of the same web. Now you can see that this definition of x also feeds that use of x. So again, they should be a part of the same web. And transitively, you can see that the web now extends not only from here to here, but goes from here to here and over here, because this definition over here is feeding this use. Similarly, this definition of x is feeding that use of x, and therefore the web now extends from this use to this definition to that use and going back to that definition. So you can see that the ones which are reaching the same use are connected together, especially those definitions in the same web, and those uses which are reached by the same definition are also connected together, and a transitive closure of all this forms a web. So you can see that unlike y, we have a big giant web of x's because this definition and those uses are all tied together. You can also see that we have another web here for x because those definitions and uses are separate and they are not tangled together with the earlier ones. You can see that this definition of x only reaches that use of x. This use of x is not reached by either of these definitions, so it is separate. And in addition, this definition of x also does not reach this use of x. It does not reach that use of x here and so on, and therefore this definition of x and that use of x is separated out and is called as web S4. So through this example you can see that how the definitions and the corresponding uses would be tied up together to form a web. A simple algorithm can be thought of which traverses the control flow graph, isolates the definitions and uses, and tries to find out which uses are reached by which definitions, and in turns which definitions are tied to which uses, and uses that to generate a transitive closure, and that forms a web. Now, having determined these webs, the next step in the algorithm for register allocation is to detect their interference. So as you can see through the previous example, each of the webs define a live range, starting at the top level definitions and ending at the lowest level uses. The same definition of interference applies here as what we had looked at through earlier example. Two webs interfere if their live ranges overlap. In other words, After determining the webs, what we will do is we'll try to take their intersection, and if their intersection is not empty, they will be overlapping. If two webs interfere, the values must be stored in different registers or memory locations. You can easily see here that when the webs interfere, you cannot give the same register to them, because if you do so, then the webs will start overwriting each other's values, and therefore wrong values will be present in those registers, and it will create problems for program semantics which will be incorrect. So just as the principle of interference says, when two live ranges intersect or they share a particular program point, they had to be in two different registers. The same principle applies to webs here. So if the two webs do not interfere, we can definitely share the same register between them, because one web would have finished its execution, and before we start the next web, that register will become free to hold the same value. Let us now revisit the same example of these webs that we found to determine what kind of interference exists. As you can see here, we have four webs, S1 going from here to here, S2, which is a big large web, is going from here to here, and here to here, and here to here. The third web that we have is also a web of X, but again, it's a different web going from here to here called S4. And then finally, we have yet another web of Y, which is going from here to here. One of the things that you will see here that has really happened is, by doing these webs, we have separated the ranges of Y, which we can allocate separately in register. For example, this range and that range of Y is separated. So we can decide what to do with this range separately and independently out of that range. Similarly, this range of X and that range of X has been separated. So one of the important things that happens when we construct these webs is the separation of these ranges. Many times the programmers might use the same variable, but they have totally different set of values which participate in them and which can be separated based on these webs. And this analysis helps us to do this separation. For example, we can choose to give a register here to Y, but we may not want to give a register to Y over here, and that separation is really important in making really good register allocation decisions which are different for different ranges. Coming back to the original point of interference, now let us see what is going on. As you can nicely see from this elegant concept of webs S1 and S2 are interfering here, because S1 spans from here to there, and S2, part of S2, is starting here and ending here. So at this particular program point, you can see that both S1 and S2 are active and are overlapping, and therefore they cannot share the same register. You can easily see here that if we give the same register to S1 and S2, there will be a big problem, because that register will load a value of Y here. The same register now we are giving towards the second web, X. So it will also load X value into the same register R1, let's say. Now what happens to the old value? It is completely lost. Now when we use the same register for getting the value of Y, R1, it is not going to contain Y, but it is going to contain X. And therefore, it will be a wrong program semantics. And that's why when the webs overlap, they cannot share the same register, because the values are going to get overwritten as shown over here. Continuing the same concept of interference, two webs interfere when they share the same program point. So you can see here S2 and S3 are going to interfere because again they are going to share the program point over here, and that's why they cannot share the same register. You can also see here, however, that S4 is not interfering with any of the webs that are over here. Similarly, S1 and S3 are not interfering either because they don't share the same program point. So only the interference is between S1 and S2 and S2 and S3. Now let's talk about how to build an interference graph from these webs. Now first thing to note is, what are the nodes of this interference graph? The nodes are the webs in this particular case, which are four different webs, S1, S2, S3 and S4. They represent different live ranges as we have found them in the control flow graph. What about the edges which are present here? The edges are representing interference. So as we saw in the previous example, S1 and S2 are interfering. So that is shown by this edge. S2 and S3 are interfering, that is shown by this edge as well. And S4 is not interfering with any of them, that's why there is no edge between S4 and any of the nodes. And similarly, S1 and S3 are not interfering either, there is no edge between them. So this is how we build the interference graph, which shows if the two webs are intersecting at certain program point. You can clearly see now, putting the control flow graph and interference graph side by side, that this is really true, because S1 and S2 was interfering over here, so we got an edge between the two, and we got an edge between S2 and S3 over here because of the interference there. S4, however, it does not interfere with any of them, and similarly, as pointed out earlier, S1 and S3 are totally disjointed from each other and do not interfere either, and that's why there is no edge here. Now the next step after we build the interference graph is to actually carry out the register allocation. Again, let's remember what is register allocation. Register allocation tells us which of the webs will get a register and which ones will not get a register. The ones which will get a register will have to make a further decision on which register to give them. Is it going to be R1 or R5 or R7? And of course, the ones which are not getting registers, we are going to hold them in memory, and when their values are needed, we are going to have to load them through explicit code, which is doing the loading of those through loads and stores. And so the next step is to allocate these webs to different registers. And we have an interference graph here, and each one of them are the webs, and these are the edges which tell us that those webs should not be in the same register. So each of the webs gets a physical register. We also call that register by a color. For example, register R1 could be yellow, R2 could be blue, R3 could be green, and so on. When two webs interfere, they cannot share the register, as we have seen earlier, because they will override each other's values. So the problem of giving registers to webs then boils down to a graph coloring problem. Two webs cannot share the same color if they have an edge. So the big question is, given this type of an interference graph, can we color it using a given number of registers that we have available in a processor? Again, recall that typically we have 32 registers available, but in embedded processors, we could have fewer ones, such as 16 registers, or sometimes it could be as small as 8. And how to fit these different webs in 8 available registers or 16 available registers therefore becomes a very challenging problem, and that problem is called as graph coloring. And so the graph coloring problem really shows how to do the register allocation. Two nodes connected to the same edge have to have different colors, and the total number of colors we are going to be able to use should be less than the number of registers that we have. Now this graph coloring problem is NP-complete. In other words, to solve it optimally, we may need an algorithm which takes exponential amount of time. Remember, while performing compilation on large programs, this time could become very high, and the compiler could become extremely slow. Now this is something which is not acceptable. Remember, many times when we compile a program, we want to be done very quickly, and we of course want to have a great quality code. So we can't simply sit there and spend hours and hours watching the screen when the compilation is going on. We need to have that compilation done very quickly. Fortunately, we have good heuristics to solve this complex register allocation problem. In order to understand those heuristics, let's first do a few examples which tell us how to go about doing this graph coloring for simple examples. So what we have here is an interference graph having 4 nodes in it, but none of them are interfering with each other, since there are no edges present in this particular graph. So the question is, how many colors are necessary for coloring it? And the answer is, we can give the exact same color to each one of these nodes since they are not interfering, and so one color is just sufficient to color this particular graph. In other words, in this situation, one register will be enough for us to hold all the values in registers so that we can save all those memory load stores. Now let's complicate this example. What we have in this example 2, again 4 nodes, but now we have an interference between 2 of these nodes. So the question is, what are the minimum number of colors that we need here to color this graph? Can we do it with one, or do we need more? The answer to this, for this particular example, we are going to need 2 colors. The reason, if we put this node in register R1, the interfering node cannot get the same register, so we have to give a different register, let's say R2, and so we have to have 2 different colors, one red and one green, because they cannot share the registers. Other nodes, however, can get either one of these colors. So we can give a red color to these 2 nodes, or we could even have given 2 green colors over here, or we could have had even one green and one red. That doesn't matter, because these nodes do not interfere with any other nodes. So they can get any color they want. Now we are going to complicate this example even a little bit more. What we have done here is we have added 2 edges, and initially in the last example we had only one edge here, but now let's say that this node and the other node are interfering. That's why there is an edge here. And similarly, this node and that node are also interfering, and that's why there is an edge here. So the question is, for this type of interference graph, how many colors or the minimum number of colors are sufficient? Is it going to be 1, or is it going to be 2, or is it going to be even higher? And the answer here, as you can see through this simple example, is we definitely can't have just one color because of the interference, but 2 colors are still sufficient for this example. How? We could do this red, this green, to take care of the interference here. This being green here, we cannot of course give this node a green color, so we had to give a different color. Fortunately, this node is not interfering with this, so we could reuse red color here, and that's why we gave it a red color. And then finally, we can't use red color over here, but since this node is not interfering with this, we could simply use the green color which is present, and that's why we could color this whole graph using only 2 colors. Now, we complicate the example even more, and what we have done here is added 2 more edges. We have added this edge between these 2 nodes, and we have added this edge between these 2 nodes. So now you can see that the graph is looking much more connected than ever. We have in fact 4 nodes, but we have 1, 2, 3, 4, 5 edges in the graph. And so the question is, how many colors are now necessary so that we can still color it, keeping the interference relation in mind? What is the interference relation again? The interference relation says that if we ended up giving red color to this node, we cannot give the red color to a node with which it interferes. In this case, however, 2 colors are not sufficient. Let's see why. If we give red color here, we have to give green there. The moment we give red and green there, neither one can be used for this particular node because this interferes, so red color is not an option here. Because this interferes with green, green is also not an option here, and therefore we are forced to think of yet another color which is blue, and that's why we have 3 colors here. On the other hand, if you notice this node, it cannot be a color which is green, so it is red. It cannot be color which is blue, which is red, and that's why we don't need any additional color over here. We can reuse the red color. The things would be different if we had interference over here, which is not the case. So in this particular case, we still can manage with 3 colors. 2 colors are however not sufficient because of this triangle. Now, having looked at the different colorings, different graph topologies, and how many colors are sufficient for which one, let us look at a heuristic algorithm of how to color a graph with n colors. As we mentioned earlier, in general, finding the minimum number of colors that are sufficient is a hard problem. It's an NP-complete problem, needs an exponential algorithm. We do not have that much amount of time when we perform compilation. We cannot sit for hours and hours there while the register allocator is trying to make these decisions. That is why we pick fast algorithms which are heuristic. Of course, these heuristics are suboptimal. In other words, many times they may not find the minimum number of colors and might carry out a register allocation that is less than optimum. So again, going back to the problem, The idea is to color an interference graph with n colors, where n is the number of available registers. So these heuristics is based on two important observations. If a degree of a particular node that we are trying to color is less than n, then what should we do? What is the degree of a node? The degree of a node is the number of outbound edges from it. In other words, the degree tells us how many neighbors this node has. So if the node has less than n neighbors, we can always color this node, because each one of the neighbors still has a unique color. It leaves a color available for this given node. For example, we have a node here and we have its degree 2. So we have node 1 here, node 2 and node 3. This is a degree 2 node. So let's say I have two different colors given to two different neighbors here. A red color is given to this node 2 and a blue is given to node 3. I still have a color available for this, which is green. So as long as my neighbors are less than n, I have a color left out for this particular node here. My degree is 2 here, and if my n is equal to 3, then I can sufficiently color this particular graph using 3 colors. So the important point to be noted here is that when the degree of a node is less than n, the node can always be colored, because even if we give out n-1 colors to the neighbors, we'll have at least one color left to color the current node. Now the second case here, what may be the case if the degree is greater than or equal to n? So in this particular case, we could have two different situations. Again, this is our node 1, this is node 2, node 3. And let us say that in this case, we have only two colors available, red and blue. Red and blue are the two colors. So let's say in this case, we give red color here, blue color there. Then what do we do with this? We won't have any color left in this particular case, and we might have to spill this node. But as you can easily see here, it would be foolish to unnecessarily use a color blue here. So what we could have done here, we could have also given this node a red color, and now we could color this particular node with blue. So you can see in this case that even though the degree is equal to 2, the neighbors can share the colors, and therefore we can still color this using 2 colors. That is case 1. Now let's take a look at a slightly more complex example here. The degree is still 2, so it satisfies this condition, degree greater than or equal to n, n is equal to 2. The question is, under this particular interference graph, can we still color this using 2 colors? And if we take an approach in which we have to give R here, the red, you can see that we cannot give the red color over here because that is going to interfere. So in other words, this red color cannot be given here because they share a node. So then what could we do? We could give it a blue here. The moment we give red and blue here, however, we have no color left for this, and therefore we have no color for this node. And in such a case, even under this particular condition, we simply cannot share colors amongst the neighbors, and therefore the node doesn't get a color. So the examples that we showed earlier showed both the possibilities. If the neighbors can share the color, then we might be able to still color the current node with n colors. However, if the discussion that we had on the previous slide shows us how to go about devising a graph coloring heuristic. The key goal of this heuristic is to first figure out all those nodes which are definitely colorable because they have degree less than n. That means no matter what happens to their neighbors, they are definitely going to have a color left out for them. And the first step that we do is we go through the whole interference graph, remove all these definitely colorable nodes that have degree less than n, and put them on the stack. So here is how a stack looks, and at the bottom we have all these nodes going over here. Remember, what we are trying to do here is all these definitely colorable nodes that we don't need to worry about, we are putting it in the stack at the bottom. And in a minute it will become clear why we are using a stack here. And so what happens when we have removed all those nodes that have degrees less than n, which are definitely colorable? All the remaining nodes that would be left out in the graph would have a degree greater than or equal to n. And now what we want to do is, amongst all these nodes that are left out, we want to find the node which has the least spill cost and remove that and push it onto the stack. So we'll take this node and push it onto the stack over here. Now the question is, why are we doing this type of stuff? You can easily see that what we want to do here is to order the stack in terms of the nodes with regard to the spill cost. At the top of this, we'll have the highest spill cost node. Below it, it will be the second highest, it will be the third highest, and at the bottom will be the least spill cost node. In other words, all these nodes now could potentially reside in the memory. And what is spill cost telling us? Spill cost is telling us the cost of putting this into the memory. So at the top, we'll have all those nodes which have highest such cost. So when we start coloring, we'll look at those first and we'll give out those registers. And as we go down the bottom, we might start running out of registers and we may not be able to give those. And therefore, all the highest spill cost nodes will get registers. Again, what is the spill cost? Spill cost is the cost of keeping that node in the memory. In terms of number of load stores it will incur, and by giving it a register we are saving that cost, and that's why highest spill cost nodes are surfacing at the top of the stack. So the previous discussion shows us that the stack is providing an ordering of all the nodes in the interference graph. The ones which are definitely colorable are at the bottom. Next are the ones which have least spill cost here, and the spill cost is rising as we go toward the top of the stack. After removing these nodes and putting it on the stack, now we are ready to start coloring or giving the registers. What we'll do in this particular process is, we'll pick up the node from the top of the stack and decide what to do with it. So in this particular case, we'll take out this node and we will try to decide what to do with it. The coloring step is very simple. If we have a color available, we'll give it to this particular node. So how do we do the coloring decision? We have to find a color that is different from its connected nodes, and if we can give it an available color, then we shall go ahead and give it. So for all these nodes which are at the bottom, this statement will be true because the degree is less than n. The color should always be available. The color will be definitely available at the top, and then as we go towards the bottom over here, we may start running out of colors, and we might have to say that too late, sorry node, you are going to go to memory. I don't have a register available for you. And what would happen in this particular process is all the nodes which have high spill cost would have already gotten the registers. The ones which will be left out will be over here, which have lesser spill cost, but whose degree is greater than or equal to n. The correct answer for this quiz is that Chaitin's algorithm results in a spill here, but Briggs does not. So this is a classic example which shows that optimism pays off and does not result in a spill, whereas pessimism is resulting in a spill. So we first understand the Chaitin's algorithm. Remember what it does. The condition it applies is the out degree of a node being greater than or equal to n. It tries to determine the least spill cost node in such situation, and it will carry out an actual spill and remove it from the graph. So in this situation, because the out degree of the original graph is equal to 2 for all these nodes, it chooses number 1, the node number 1, which has the least spill cost, so to say, will remove it and carry out a spill here. So that's why Chaitin's algorithm results in a spill. Let us try to apply Briggs' algorithm to the same graph now. What Briggs' algorithm says is, if the out degree of a node is greater than or equal to n, where n is the number of registers, be optimistic. Don't assume that it will result in a spill, but go ahead and pick up the least spill cost node and put it at the bottom of the stack first and remove it from the graph. So in this case, assume that it was node 1. So we removed the node 1 along with the 2 edges that were incident and put it into the stack here as shown. Now we got the remainder of the graph, and there are 2 potential candidates here which have degree less than n, 2 or 3. So we can pick either one of them. So in this case, let's assume that the Briggs algorithm picked node 3 to be pushed on stack and removed the incident edge over it. So now we can see that the remainder of the graph is consisting only of node 2 and 4. Again, in this particular case, we have a choice of picking either node 2 or node 4. So again, assume in this particular case, node 2 was picked because both of these degrees were less than n. So the Briggs algorithm picked 1 and pushed it onto the stack. And then finally, we have node 4, which has degree 0, which will be pushed onto the stack as well. And here is how Briggs algorithm has simplified the whole graph. Picked up node 1 first, whose degree was exactly equal to n, and which was the least spill cost node, but it assumed that optimistically it will get it a register and pushed it, and then it removed the other nodes as explained and pushed them onto the stack. So the whole set of nodes now is on the stack. No spill decision has been made yet, and now what Briggs algorithm will do is will take these nodes one by one off the stack and assign it a color if available. So what it has done is taken off node 4, which was at the top of the stack, and gave it a red color, one of the available colors here. The next thing that it will do is take off node 2, which is at the top of the stack, and give it a available color. So in this case, node 2 is adjacent to node 4, and so it must get a different color. It got green color here. Next, it must take off node 3, which is at the top of the stack, and give it a color. And so what happened was node 3, now being adjacent to 4, should get a different color, which is green in this particular case. And finally, it will take off node 1 and give it an available color. Let's see if what happens. This is the important one. Whether it will result in a spill or whether it is going to get a color. What do you think? And if we do that, when node 1 gets back into the graph, it is adjacent to node 2, so it cannot get green. And it is adjacent to 3, so it cannot again get green. But it definitely had an available color to it, which is red. And therefore, the graph is now colorable as per Briggs algorithm using two colors, red and green, whereas in Chaitin's case, he made the pessimistic decision on that first condition, took out the least spill cost node, and went ahead and spilled it. And you can see that in practice, we could have colored it, and therefore Briggs algorithm is superior. It eliminates a spill when it can, being optimistic. So the lesson here is optimism pays off. Folks, I presented to you two different algorithms. Chaitin's, which is pessimistic, which assumes that there is a spill on that condition being met, number of edges, outbound edges, greater than or equal to n, where n is the number of registers. On the other hand, Briggs is optimistic, and he pulls out the least spill cost node, pushes it on the stack, removes it from the graph, and keeps repeating this particular process and pushes all these nodes on the graph, and at a later point worries about the coloring by taking them one by one and seeing if a color is still available for them. So having understood these two different algorithms, now let us test our knowledge if they are the same or they are different, especially on an important graph that we encounter in practice. So here is a graph which is called as the diamond graph, and here is a question. For the following interference graph, do the coloring using both pessimistic Chaitin's coloring algorithm and Briggs optimistic algorithm result in spill? Assume number of registers to be equal to 2, one red and one green. And which of the statements is true with regard to these coloring algorithms? Both algorithms result in a spill for the enclosed graph. Chaitin's algorithm results in a spill, but Briggs does not. That is the second statement. The third statement is Briggs' algorithm results in a spill, but Chaitin's does not. And the fourth statement is neither algorithm result in any spill. So please apply Chaitin's algorithm, the pessimistic one, the Briggs algorithm, optimistic one, to this diamond graph and mark the answer that is correct among these four choices. So students, having seen the algorithm for performing graph coloring, which bases pushing things on stack and then popping them back and giving it a color. Now let's look at a simple example and see how the coloring actually takes place. What you have here is an interference graph of 5 webs, S0 through S4, and we have the interference edges which are shown over here, and we got 3 colors or 3 registers to color this particular graph. So let us now see how the actual algorithm works on this particular graph for coloring it. So as you know, the first step is to pick up all those nodes whose degree is less than n and push them on the stack. So as you can see here, we have selected node S4 because its degree is 2, which is less than the number of colors we have, which is equal to 3. And we have removed it from the interference graph and pushed it onto the stack. After this, now we have S2, whose degree has fallen below 3. The degree is now equal to 2. So we have removed it from the interference graph and pushed it next onto the stack. So you can see that the nodes that have been pushed are definitely colorable because their degrees are less than 3, and that's why they have gone on the stack. Next, we have node S1, because after removing S2 and S4 and all the incident edges, you can see that the degree of S1 is now 2, and it has fallen below n is equal to 3, and that has gone on the stack. And that's the next node, which is to go on the stack. After removing S4, S2, S1, all these edges have been removed. So we had a choice of either S3 or S0 because their degrees are now just equal to 1. So in this case, we have picked S3 and pushed it onto the stack. And then finally, we have removed node S0. Its degree has fallen to 0 and pushed it onto the stack. So you can see that the stack was started with those whose original degrees were less than 3, such as the node S4. And then after removing those nodes, those whose degrees became less than 3, they were taken out and they were pushed, and the process was repeated finally, and the node S0 was pushed on the stack. So this particular process of arranging the nodes of the interference graph on the stack in terms of their degrees is called as graph simplification, and tells us that we ought to give the colors in a particular order so that the colors are always available for those nodes which are deep in the stack, and so the colors should be given out for those nodes which are at the top, and that's why we are using a stack. Now we have 3 registers, as I mentioned. Let's call them as blue, green, and red, and let's try to give the colors to these nodes in the next step. So the first node, S0, is now removed from the stack and is given a color which is blue. The next node that will be removed will be S3. And so we remove the next node from the stack, S3, and now we have to decide its color. Now as you can easily see here, it cannot be blue, but we have a choice between green and red. And in this case, we are going to color it with green. The next node that is to be removed is S1. And now you can see that S1 is interfering with S0 as well as S3. So it cannot have a color of either green or blue. And so the choice of color is red here. And what we have here is a color red for S1. Next, the node to be removed will be S2. Now you can see that the choice of color for S2, it cannot be red, it cannot be blue. So what it must be? The remaining one, which is green. So now S2 got a color of green, and then finally the last node to be removed here is S4, and again we'll have a color choice here. Well, it cannot be green because it will interfere with both of these. So it could either be red or it could be blue. And in this case, we have decided to color S4 as blue. So as you can see that by systematically trying to give out those colors to those nodes which were interfering with lots and lots of things which came at the top of the stack, and those which were not interfering with many and whose degree was less than n, which came at the bottom, we were able to put an ordering on this interference. Now let us complicate this previous example, adding yet another interference to it from S2 to S3, and let us see what happens, especially when we have the same number of colors available, whether we are able to color them or something else happens here. So let us walk through this example, again applying that algorithm that we saw, by removing all those nodes whose degree was less than n and putting them at the bottom and then building up towards the top of the stack after removing those nodes. So again, the first node that we remove here whose degree is less than n is S4 because its degree is 2, which is less than 3. And so that is the first node that is picked up by the algorithm and removed from the interference graph and put it into the stack. As you can see here, no other node meets that condition because everybody's degree is greater than or equal to 3. For example, S0's degree is 3, S1's degree is 3, S3's degree is 4, and S2's degree is also 4. So none of them could be removed with that particular condition, and only S4 could be removed and is put into the stack. Now after we removed S4, you can see that all the remaining nodes, let's look at them carefully. S2's degree is now 3, S0's degree is also 3, S3's degree is 3, and S1's degree is also 3. So in other words, we cannot remove a node whose degree is less than 3 in this particular case because all of them have the degree equal to 3. So in such a case, we cannot put a node onto the stack, so we had to make a decision here in terms of what to do. The algorithm that we saw earlier would try to pick a node with the least spill cost and put it into the stack. By removing that, we'll keep proceeding, and then we'll do the next node whose spill cost is a little bit higher, and we would order the stack with the highest spill cost node. That is one option to proceed. And that algorithm that we saw on the earlier slides is called as the optimistic algorithm because it still hopes that even though everybody's degree is greater than or equal to n, they might still get a color because their neighbors may have the same color. Whereas a different version of the algorithm assumes, which is called as Chaitin's algorithm, that the node will not get any color and therefore it should be decided that it should be spilled and removed from the graph. So if we use that Chaitin's algorithm, which when run into this condition of everybody's degree greater than or equal to n, will pick the least spill cost node and actually go ahead and spill it, remove it, that is not give it a register, then we would take out S1 in this particular case from the graph and remove all its edges. If we were to proceed on the lines of the Briggs algorithm or the optimistic algorithm, we would have put S1 onto the stack and worked out the example exactly the same way as example 5. So let us now work out this example using Chaitin's assumption, that is, S1 is not going to get a register and it is the spill cost node, and so let us spill it and remove it from the graph. If we do that, then this is the graph which we will see where S1 is removed. And next, we'll try to pick out a node whose degree is less than or equal to n from the remaining graph, which is S0, S2, and S3, and we will try to put it onto the stack and then proceed with the algorithm. So what we'll do next is, after S1 is being removed as a spill node, that is no color is given to it, it is completely to be held in memory, we'll try to decide between S3, S0, and S2 as the next node to be pushed into the stack. And let's say S3 happened to be that node because its degree is now less than n, and we have gone ahead and pushed it into the stack like this. Next, as you can see here, we have a choice between S2 and S0, and in this particular case, we have decided to just pick randomly S2 and put it into the stack as the next node which should get a register. And then finally, we have removed the node S0 because that is the remaining node and pushed it over here. So again, what is this algorithm doing? It started by pulling out a node whose degree is strictly less than n, that happened to be S4. So the first node to come off the stack here is, which is at the top of the stack, S0, and we put it in the interference graph, and we have a choice of colors, and in this case we decided to give it red. The next node will be S2. This S2 now interferes with S0, so obviously which color cannot be given? It cannot be red. So we have a choice between blue and green here, and we decided to give a green color in this particular case to S2. The next node that is to come out will be S3. So in this case, S3 is again interfering with S0, so it cannot be red. It could either be blue or green, and in this case, we decided to give it a blue color. Finally, the last node to come out of the stack was at the one which was at the bottom, S4, and as you can see, it is interfering with S2 and S3, so it cannot have either of the blue or green, and so we'll give it a red color, and that's exactly what happened. And this is the final coloring of the graph. And so we can see that the node which did not get any color, which we decided not to even consider for coloring, was S1. It has been spilled to the memory. In other words, it will be loaded and stored out of memory whenever it is referenced. You can see that this algorithm pessimistically assumed that S1 will not get a color at this point when we ran into it and decided to spill it. But let us now look at, would S1 get a color if we had not done that at that place and pushed it into the stack under that optimistic algorithm which we saw earlier, which always removes a node and pushes it in the stack and then worries about whether it will get a color or not? Well, in this particular case, you can see that S1 interferes with S3, S0 and S2. So none of these three colors would work for S1, and so even under that algorithm, S1 would be spilled to the memory. So it is not always that pessimism and optimism perform equally well or equally badly. There are graphs for which the optimistic algorithm, which pushes the node onto the stack with a hope that it will get a color eventually, it will perform better than the pessimistic one, which decides that it is hopeless and let's go ahead and spill it when the degree greater than equal to n condition is reached. Pick the lowest spill cost node and go ahead and spill it. That particular algorithm will underperform the optimistic algorithm. We're going to do a quiz pretty soon to illustrate this, so stay tuned. So students, now let us test our knowledge of graph coloring by looking at a special type of a graph called clique. So here is a question for you. A clique of size k is a completely connected undirected graph of k nodes where each node is connected to the remaining ones. What is the minimum number of registers necessary for coloring a clique consisting of k nodes? Please write your answer in the text box below. To illustrate this, I'm drawing a clique of size 3 here to help you figure out your answer. This is my clique of size 3, 1, 2, and 3 nodes, because you can see that each node is connected with the rest other two. For example, this node is connected to these two, this node is connected to the other two, and similarly it's true with the last node, it's connected to these two. So this is a clique of size 3. The question is, how many colors are necessary here? Minimum number. And please go ahead and mark your answers now. As you can easily see through this example, we would have needed 3 colors here, and so the colors that are needed for a clique of size k is k registers or k colors. Remember, because each node is interfering with the others, each one needs a separate color, and there are k of those, therefore we need k colors. So we saw that the optimistic and pessimistic algorithms try to give colors to nodes by ordering them in the stack and pulling them out of the stack and then assigning them colors. The pessimistic one runs into that condition greater than equal to n and immediately causes a spill, whereas the optimistic one postpones the spill by pushing it into the stack and hoping that the spill may never happen because the neighbors will get the same color and therefore there will be a color available. But when the coloring fails and a spill is caused in either one of the algorithms, then what are the options? So the first option is you pick a web and allocate value in memory. In other words, what do you do here? You either under the pessimism or optimism decide to cause a spill and just never give any color to that node and load store that value from the memory. All the definitions go to memory through stores and all uses come from the memory through the loads. But wait, there is still one more option that is remaining which can still try to give the registers to a part of the web, and the option there will be to split the web into multiple units. In such a case, part of the web or part of the live range will get a register and part of it will be denied a register. So in such a case, after splitting, we'll retry the coloring as per the original algorithm. So for splitting, the question is which web to choose? Well, one of the choices is take the web which is interfering with the other webs the most, that is, whose interference degree is greater than or equal to n, and take the one which is the minimal spill cost. So the rationale here is by removing this web and splitting it into pieces, we would be able to reduce the interference for many other nodes, and since this has the minimal spill cost, we'll be able to use a part of this web in the register, and even if a majority of it does not get a register, will still not be heavy in terms of the load stores. So what is the spill cost? Again, this is the number of load stores that we incur by keeping this web in the memory, and by keeping the minimal spill cost node into memory, we will have minimal number of extra load stores. So let us discuss a little bit about the spill cost now. What is an ideal measure of the spill cost? As you know, the program executes and the number of actual load stores will be those which are dynamically executed. We can't, of course, compute this when we compile a program, so we have to do some estimation here of the spill cost. What are the reasons we can't actually exactly compute the dynamic spill cost? Because we don't know the control flow and we don't know which way the branches execute. There will be more nodes under one side of the branch than the other, and unless we actually execute the branch at execution time or runtime, we will not know the exact number of load stores that will execute. Second reason could be that a load stores are inside loops, which is a very common occurrence. And we don't know how many times the loop will execute, and therefore we will not know how many times those load stores will execute. Third is the execution cost, or the number of times the load store executes, may be sensitive to input data and will be different for different executions. And so finally, what we want to do here is use a static approximation to find out what is the cost of these load store. And there are two approaches to these. One is using the profiling, which gives instruction execution frequencies. The second one is to use heuristics based on the structure of the control flow graph. The second technique is what is predominantly used in practice, and it gives you a relative estimate of the spill cost, which is important, rather than the exact count of the spill cost. And the relative estimate tells one whether it is worthwhile spilling a web 1 versus it is worthwhile spilling a web 2 based on these relative spill costs. So let us see the second technique, how it works roughly. The goal is to give priority to the values which are used inside the loops and weigh them more. We typically assume the loops execute 8 or 10 times. So having given the loop an estimated execution time, what we do next is find out the nesting level of the loop and calculate the cost of store by using an estimated execution time of the loop. So for example, if we have d-nested loop and each of the loops executes 10 times, then we have 10 to the power d executions of the loop in total. We'll multiply that by the cost of a store instruction to get the store cost, and we'll multiply that by the cost of a load instruction to get the load cost. So 10 to the power d gives us total execution frequency of the loop nest, which is d-nested. That is, there are d loops which are there inside one another. After computing these types of costs, you can see that those webs which are in the deeply nested loops will get registers than the ones which are in the shallower parts of the loop, and therefore will have less number of dynamic spills eventually. In this particular way, we do not have to know exact dynamic execution frequency, but we can use the nesting depth and an estimated execution time of the loop to bias the spill costs for those webs which are in the deep loop nest over those which are in the shallow loop nest. Let us look at a simple example of spill costs in a simple control flow graph. This is the entry or header block which is outside the loop. Then we have a simple loop going on here, and then we have an exit block, and we have live ranges or webs which span across these. You can see here that we have a web on X spanning from here to there, and we have a web which is spanning from here to here on Y, and the same web then extends over here. So we have a web of X and we have a web of Y. In particular, the web of Y is partially inside the loop nest. Now you can see that the spill cost of X is very straightforward because all of their occurrences are outside the loop nest. So it is really the cost of store over here and the cost of load over here, which is the spill cost. This is the cost we'll pay if X to be allocated in the memory. However, the spill cost of Y, as you can see here, now that the Y is inside the loop, is going to be 10 to the power 1 because this is a single nested loop, and we have a store of Y and a definition point of a Y over here. So that is the spill cost of Y inside this loop nest. In addition, we'll have a store of Y here and a load of Y here, but those will not be biased by multiplication by 10 because they are not inside the loop nest. So roughly we can assume that the spill cost of Y is the one which is inside the loop, and that happens to be given by 10 times store cost of Y and 10 times load cost of Y. Now with one register, which variable gets spilled? Obviously, the one which is the least spill cost. And so in this particular case, it will be the X which will be spilled. Now we mentioned that when we are faced with a spill decision, we are going to go ahead and split the web so that at least a part of it can get a register and part of it will be executed out of memory. So what we will try to do in such a case is split a web into multiple webs so that there is a least interference in the interference graph and it is n-colorable. Typically, the web which has the highest amount of interference and the least spill cost will be the one which will be chosen for splitting. After splitting it, a part of the web will still be spilled, and what we will do is we will spill the web or store the value into the memory and we'll load it back at the points where the web is split. So in other words, part of the web will be stored and loaded from memory and the other parts will stay in register. So now let us illustrate the benefits of splitting through a simple control flow graph which is shown on the left side here. What we have here is 3 different webs, one on Z, another one on X, and third one on Y. As you can see here, the web on Z is extending through this particular loop and is interfering with the web on X and Y. Let us go ahead and first draw the live ranges here for these webs. The first live range or the web starts with the definition of Z, extends through the use of Z, and extends all the way through the loop and ends at the use of Z here. The second web, which is on Y, starts over here at the definition of Y and ends at the last use of Y, which is over here. And the third one, which starts at the definition of X, ends at the last use of X over here. So you can see that these 3 webs are clearly interfering inside the loops. However, they are not interfering at every point of the program, and so we can take advantage of that. Here is the interference graph that is shown for the whole program, in which X is interfering with Y, X is also interfering with Z, Y is interfering with Z, and Y is also interfering with X, and finally Z is interfering with the other 2. So we have here a complete graph of 3 nodes which are interfering with each other, and so we will need definitely 3 colors for coloring them, because this happens to be a clique of size 3. So given this clique of size 3, is it 2 colorable? It is not, because we are going to need at least 3 colors for coloring this, 3 distinct colors. So here is why we will carry out a splitting here. What we will do is, wherever there is no use of Z in this particular interval here inside the loop, we'll split Z around that particular point. we'll leave x and y as they are. Those live ranges are inside the loop and we'll leave them as they are. However, the live range of z, which is live across the loop but has no use of z inside, will be split at these 2 points. If we do this splitting, here is how the interference graph changes. Let us say this part of web is called z1 and this part of web is called z2. X and y still interfere with each other, but these parts of z do not interfere now with anything else, and the graph is simple. Now you can see that this graph is 2 colorable as follows. We can give one color to x and another to y, and we can pick any color that we want to be given to z. And so with these 2 colors, blue and red, this graph of split web is 2 colorable. We could have also given z this blue color. In this case, we have given it red color. And if we look at the registers that are given out here, this is how they look. So we have given this red or R1 to Z1, and the same register is given to Y at this particular point. And once Y's use is over, we give it back to Z at this particular point. So what we'll have to do here is to be able to put a store on Z, store the value of Z here, and we'll have to put a load to get the value back for Z over here. And those are the boundary load stores. They execute outside the loop. They do not have significant costs, and that's how we can adjust for reusing the register. Because remember, if we do not save it and we just overwrite it here, we will lose the value of Z. So we'll have to store it, which is a spill store and a spill load. Having seen the splitting through an example, now let's take a look at a simple heuristic that is often used in terms of splitting. First, we identify a program point where the graph is not R-colorable or where the number of webs exceed the number of available registers. Next, we pick a web that is not used for the largest enclosing block around the point of the program. For example, in the last example, we saw that Z was not used during that loop, and so that's how we pick that web. We go ahead and split that web at the corresponding edge on the entry of that region. Then we'll redo the interference graph, and then we'll try to recolor it. As you can see here, the interference graph in the previous example was simplified heavily because of split of Z into Z1 and Z2, and now it became 2 colorable. Now splitting has one more nuance in terms of where to exactly split a node or a web. When that decision is being taken, one has to weigh upon cost and benefits. So cost of splitting that web at that particular point is incurring a store, and therefore is proportional to the number of times the split edge has to be crossed dynamically, because that is the number of time that store will execute. Now remember that store is not present in the original live range, which is not split, because the value need not be stored into the memory. So this is an additional cost due to splitting of that store which is inserted. Just like there is a cost of that store, remember at the bottom where the range again becomes live, there is a load which is inserted at the bottom of the range to get the value back into the register, and the number of times that load executes is another piece of cost that is incurred. So the number of times these edges are crossed is the dynamic cost of that store plus dynamic cost of this load, which is the total cost paid additionally for splitting. What is the benefit? The benefit is the increased colorability of the nodes the split web interferes with. For example, X and Y it was interfering with, and they became colorable, and we could fit them into 2 registers. And the total cost of such load store saved is the benefit side of this. Now using this cost and that benefit, we are going to be able to come up with a greedy heuristic and pick the live range with the highest benefit to cost ratio to be split. So if we have multiple choices of live ranges to be split at multiple program points, the decision will be based on this benefit to cost ratio. If a splitting is saving lots of load stores for interfering ranges in deep nested loops, and it does not have a high cost because the compensating store and the compensating load which restores the value there are relatively taken few times, then the benefit outweighs the costs, and so those are the ranges which will be picked for splitting. Some other aspects of register allocation which are important and worth mentioning are register coalescing, which will try to merge the live ranges against splitting them. That is one. The second one is register targeting or pre-coloring, giving them colors because they definitely are very important and they have to stay in a specific register. The second one is pre-splitting as against splitting during coloring. And the fourth one is interprocedural register allocation. So let us take a look at what is called as register coalescing. In many instructions, we have register-to-register copying. That is mainly because of multiple reasons, such as procedure calls, assigning the actual parameters to the formal parameters, many copy instructions that are not removed by the compiler, and so on. So the goal here is to reduce or remove these register copy instructions. And the key idea is if Sj and Si do not interfere, then combine their waves into one and give one register to them as against two different registers. The key goal is to reduce the copy instructions, but one has to watch out because now the range is becoming quite long and may increase the interference of this combined node and make the graph more dense in terms of interference edges. An original graph, which was colorable, may become uncolorable, and therefore coalescing has to be done extremely carefully. The second important optimization that is done is called as pre-coloring. So some variables need to be in special registers at a given time. For example, the arguments to function and return values. And idea is to pre-color those webs and pre-allocate them across function calls so that they are found in the right registers. And we are going to also avoid here the copying between different registers. And this step is called as pre-coloring, which removes the need for coalescing later. The second optimization is called pre-splitting the webs. Now you can see that some live ranges may be very sparse. In other words, they could have large regions within them, which are heavy loops, where there are no uses of those values, and therefore that range is effectively dead there. In other words, if there is no use of a variable during these large heavy loops which are a part of the live range, then we could break up those live ranges a priori. We'll have to pay a small cost at the entry point of such a region, which will be typically outside all those heavy loops. But then the graphs within those loops will be easy to color, and effectively it will save all these iterations in deciding what to split so that the graph becomes colorable, and that's why this transformation is called as pre-splitting. And so in such cases, the benefit of splitting is so pronounced that we will carry out the splitting ahead of time without waiting for coloring to tell us when to cause the splitting. Some other strategic locations which are typically used for such breakup is at a call site, because we know that the new set of registers are going to be allocated in a totally different way, and some registers which are meant for global variables will never get used inside those calls because there is no reference to those globals. So such splitting can be done at such call site. And the second possibility of splitting, as we mentioned earlier, is around a large loop nest in which is reserving those registers for those values which are declared and used within the loop nest. The language such as C allow one to declare loop local variables, and typically registers are given to those, and those are the premier candidates where the live ranges which are live through but no uses within those loops can be split. So student, let's test our knowledge now after seeing all different kinds of register allocation ideas. The last idea that we are going to test our knowledge about is live range splitting. So the statement is live range splitting always a good idea, true or false? Please go ahead and mark your answers now. And the correct answer is live range splitting is not a good idea always. That is, the statement is false. It might be counterintuitive to think this way, but as you can imagine, live range splitting also has a cost associated with it. In live range splitting, we have to associate boundary load stores. Remember, we have to put the values back into memory and then restore them back at the end of the free range. If we do this, the cost might outweigh the benefits, and so live range splitting may not be always a good idea. Many times, however, the benefits outweigh the cost, and it so turns out that the live range splitting is good, but not always. Final topic which we are just going to mention briefly and talk about is interprocedural register allocation. Remember, every procedure call or function call is considered separately for register allocation typically, which means that the registers are shared across functions, and therefore we must save and restore all the register across procedure or function call boundaries, and this is very expensive. This is especially true for programs with small functions or small methods, because for even such small methods, we have to save all the registers before we enter them, because they will be used inside those functions with new values, and they would override those values coming from outside. So before the call happens, all the registers at the caller side had to be saved, and that's a tremendous amount of cost. The calling conventions many times are too general in terms of which register to pre-color, and that doesn't solve this particular problem. And so the final resort is to do customized register allocation by considering both caller and callee together and maybe creating what is called as a clone version of a function. What is a clone version of a function? It is a specific version of a function which is effective only at that call site, which has a specialized register allocation with regard to the call site. So if foo function foo is called multiple times in the program, each will have a different invocation at a call site and will link to a different implementation of foo as per the register allocation done at the call site. We have covered a lot in this lesson. You should now be familiar with some very important concepts such as register allocation, what is a web, what is an interference graph, what is meant by colorability, and finally, what is meant by splitting a live range.